Hello, in this video we are going to solve an exam question about mathematical induction. The question has 3 parts, and as you can see most of the marks are on the third part where we actually have to prove a statement by mathematical induction. The other 2 parts, 2 marks each, are just helping us prepare for that induction proof that we have to do at the end. In part A we have a statement about non-negative integers that we want to prove, and it will be tempting to try to prove that by mathematical induction, but that's definitely not what we have to do since this part is only 2 marks. So the statement that we have to prove over here is that if you have 1 divided by square root of n plus square root of n plus 1, that is going to be the same as square root of n plus 1 minus square root of n. And that's for all n greater or equal than 0 in the set of integers. So what the approach that I think will work here very efficiently is to try to rationalize the denominator in the left-hand side. If we multiply and divide by the conjugate of the expression we have in the denominator, so we multiply and divide by square root of n minus square root of n plus 1, so we are going to have square root of n minus square root of n plus 1 on the numerator, and then in the denominator we need to consider square root of n squared minus square root of n plus 1 squared, and this is going to be n minus n plus 1. So the n's are going to actually cancel, and we are going to have here a negative 1, which implies that we can just change the sign of the numerator and write the square root of n plus 1 minus the square root of n, which was what we wanted to prove. Now for part B, there is an inequality that we want to prove, and the question states, hence show that blah blah blah. This hence over here is saying that to prove it, we have to actually use part A. But if you look at the left-hand side of the equality we're trying to prove, square root of 2 minus 1, well, that's actually square root of 2 minus the square root of 1, that's the same. And that looks like the equality that we just proved if we let n be equal to 1. So according to part A, what we will have is that square root of 2 minus the square root of 1 is equal to 1 over square root of 1 plus the square root of 2, which is 1 over 1 plus the square root of 2. Now what we would like to see is that this is in fact less than 1 over square root of 2. And this is actually true because we can see here that we are comparing two fractions where the numerator is the same, is 1, and in one of them, on the left, the denominator is larger. So when we divide by a larger number, that results on a smaller fraction. So this is as well true. So now that we proved parts A and B, we are going to focus on the mathematical induction. I'm going to write the formula again here on the side. We have the sum from r equals 1, and then it says to r equals n. I think sometimes we use a notation that just we write n on top, and then the terms that we are summing are going to be of the form 1 over square root of r. And we want to see that that sum has to be larger than square root of the last number we are summing, so n. I can write this using instead of the sum notation just dot dot dot. So when r is equal to 1, I'm going to have 1 over square root of 1 for the first term. For r equals to 2, we're going to have 1 over square root of 2, and we keep summing like that. And then the last term is going to be 1 over square root of n. We want to see that that's greater than the square root of n. And we want to see that this is true for n greater or equal than 2 and n an integer number. So that's what we are trying to prove by mathematical induction. And the first step is going to be to prove the base case. So the base case in this case is when n is equal to 2. So we are going to be summing only two terms. It's going to be 1 over square root of 1 plus 1 over square root of 2. That's all the sum has. And that we want to see that is greater than square root of 2. Well, this is what we want to see. This is true if and only if the first term on the left-hand side is just 1. So we want to see that 1 plus 1 over square root of 2 is greater than square root of 2. And if we subtract 1 on both sides of the inequality we're trying to prove, what we have is that this is true if and only if 1 over square root of 2 is greater than square root of 2 minus 1. And this is true because this is exactly what we proved on part B. So part B just helps us show that the base case holds. Now we have to do the inductive assumption. So we are going to assume, and it's important that you write that we are assuming this, that the statement is true for an integer greater or equal than 2 that we call k. So assume true for k, and this means that if we are summing, I'll write it with the sum notation, the terms are going to be 1 over square root of r, and we are summing from r equals 1 to k. This has to be greater than square root of k. This is what we are assuming to be true. And now we are going to use this assumption to prove that the statement is true for the next integer, so true for k plus 1. So in this case, we are going to have the sum of the same type of terms, 1 over square root of r. R is going to start in 1, and now it's going to end in k plus 1, and we want to see that this sum is greater than square root of k plus 1. So this is what we would like to prove. So we're going to start by writing the left-hand side, so the sum from 1 to k plus 1 of 1 over square root of r. And actually we're going to split the sum into parts as we usually do. On one hand, we are going to sum from 1 to k, and then we are going to add the last term, that is when we consider r equal to k plus 1, so it's just 1 over square root of k plus 1. And why did we do this? Because this first part of the sum, the first k terms, this we are assuming to be greater than k. This is our inductive hypothesis right here. So we can write that our sum is greater than square root of k plus 1 over square root of k plus 1. So what we want to prove is, or it is enough for us to prove that what we have over here, square root of k plus 1 over square root of k plus 1, we want to see that this is greater than square root of k plus 1. If we can prove this, so if this part over here is true, then we will have that the sum we started with on the left-hand side is greater than square root of k plus 1, which is what we want. So let's see. Can we check that square root of k plus 1 over square root of k plus 1 is greater than square root of k plus 1? This is what we are asking if it's true. If it's true, we are done. This is true if and only if 1 over square root of k plus 1 is greater than square root of k plus 1 minus square root of k, rearranging the terms. But what we have on the right-hand side is the same we had on the right-hand side on part A over here, just written in terms of k instead of n. So by part A, this is equal to 1 over square root of k plus square root of k plus 1. That is, our inequality is true if and only if 1 over square root of k plus 1 is greater than 1 over square root of k plus square root of k plus 1. But this is similar to the reasoning we had in part B. We can compare the fractions we have, or we can even multiply by the denominators and say that this is true if and only if square root of k plus square root of k plus 1 is greater than square root of k plus 1. And that's true because the square root of k is greater than 0. So we prove what we wanted to prove for k plus 1. Now we are almost done. We just need to write the conclusion. Since the statement is true for n equals 2, that was our base case, and assuming it's true for k, we proved it for k plus 1. By the principle of mathematical induction, we conclude that the statement is true for all integers greater than or equal than 2. And now we are done with the problem.